All right, this is part 2. We're going to start with some derivatives here. So take a second, see if you can figure out what these derivatives are. So obviously this has got a lot, almost everything we could possibly want to do in a derivative in it. It's going to start as a chain rule. 3 is the outside, so our derivative would be 3 times everything inside as is. So we're not doing anything to that yet. To the second power times the derivative of what's inside, and each one requires its own separate thing. So derivative of natural log is 1 over x. Derivative of e is e again times the derivative of that exponent, which would be 4. And you can put that 4 in front if you want, it doesn't matter. And then we have derivative of cosine, which would be negative sign, so that negative and this negative would turn into a positive. Keep the 5x the same, times the derivative of 5x, which would be 5. And again, that could be put in front there if you wanted. So that whole thing right there is our derivative. Again, I wouldn't anticipate something quite that big on your exam, but at least that kind of covers some of the big stuff that we've done, chain rule and whatnot. This one's got a quotient rule in it. So quotient rule for sure is something you should have on your note sheet. Just in case, again, you need it and you kind of blank a little bit. It's going to be bottom times derivative of the top, which would be 1/2 x to the negative 1/2, and you can write it like that, or you can drop it because of the negative, make it square root because of the 1/2. Sometimes if you have to do something with it, that's a little bit easier, but either way is fine. So bottom times derivative of the top minus top, I'm going to write it as x to the 1/2. Times derivative of the bottom, which is 2 times x plus 3 to the first, times the derivative of the inside, which would be just 1, over the bottom squared. X plus 3 squared would be x plus 3 to the 4th. Okay, and that's fine. You don't have to simplify this, even though you could maybe pull an x plus 3 out and knock it down. They're not going to ask you to do any simplifying this year because they don't have a whole lot of time, and they really just want to see how well you do in calculus. Here's another one where we're going to try to get an equation for a tangent line at 2. Why don't you pause and see if you can do that. So anytime we see equation of a tangent line, we're thinking point and we're thinking slope. So for our point, we know that 2 is the x-coordinate. We need to figure out the y-coordinate is. So we're going to go g of 2 equals 2 plus 2 times 2 squared times f of 2. And that's going to give us 2 plus 8 times 5. I don't know why I have 2 plus signs there. And that's going to give us 42. So that's our point. Okay. Now I need the slope. In order to do the slope, I need the derivative. So let's take the derivative of this. That's going to be 1 plus. Now we have a product rule here. So derivative of the first is 4x, leave f of x alone, plus 2x squared times the derivative of f of x, which is f prime x. Okay. And then we're going to put 2 into that. So it's 1 plus 4 times 2 times f of 2 plus 2 times 2 squared times f prime 2. This is going to give us 1 plus 8 times 5, which is 40, plus 8 times f prime, which is negative 24. This is going to end up with a slope of 17 then. Put it together, y minus 42 equals 17 times x minus 2. There's our tangent line. If they said now approximate, say, g of 2.1, we could put 2.1 in for x and work this out and get an approximation for it. But this is hopefully point, slope. We've done so many of that. That should be automatic for you if you're asked to do that. Implicit differentiation might be something you're asked to do. So why don't you pause and see how you do on this one here. So implicitly, we're just going to kind of go through the line and do each one. And when we do a y, we have to tag on that dy dx with it. So derivative of 3x squared would be 6x. Derivative of negative 4y would be negative 4 times derivative of y, which is dy dx. And then this is going to be chain rules to start with. Derivative of sine is cosine, leave x, y alone, times the derivative of xy, which is now a product rule. So derivative of x is 1 times y as is, plus x times derivative of y, which is dy dx. Okay. So then our job is to try to get dy dx by itself. Probably what we want to do is distribute here. It looks weird, but what I think we would want to do. So we're going to get y times cosine xy plus, and I'm going to just put x cosine xy times dy dx. All right. Now, our next job is to get dy dx terms to one side and everything over to the other. So I'm going to add this over, bring that over to this side. I'm going to subtract this, bring this over to here, so that we have 6x minus y cosine xy equals, and when this comes over, it's going to be a plus 4 dy dx. Now, what I'm going to do next then is pull that dy dx out. So we'd have x cosine xy, the thing that's in front of here, and then plus 4, and then dy dx factored out. Again, it's adding this over and then pulling the dy dx off. And then the last thing we're going to do is just divide by that. So I'm going to write this here, cosine xy plus 4, and we can erase that, and there's our dy dx. All right, so that process we've done before. How much of that would they ask you to do? I can't tell you. This probably is a little more than you'd be asked this year, but we're ready for hopefully anything they might throw at us in that. So here's another one of those tangent line approximations. This gives us a graph here, or a table of values. We're supposed to approximate f of 4.8 and then tell whether it's more or less than the actual function. So why don't you go ahead and pause, give it a try on that. So we need to build this out. So again, I'm thinking point and slope, just to kind of keep myself organized. I know the x value is 5. When x is 5, the function value is -3, and it has a slope of 2.5. So y plus 3 equals 2.5 times x minus 5. I'm supposed to use that now to approximate f of 4.8. So we're going to put 4.8 into there. So y plus 3 equals 2.5 times 4.8 minus 5, which is a -0.2. You're going to have a calculator this year, so definitely have that ready to go. If we do this, we should get -0.5. If we subtract 3, we should get y equal to -3.5. That's our approximation. Okay? And then it says, if f double prime is less than 0, is this more or less than your actual value? Well, if f double prime is less than 0, that means we're looking with a concave down graph. And if I use a tangent line and I work either side of it, that tangent approximation is going to be something more than the actual value. This is the actual value right here. This is the approximation. And so our approximation is more than, because f of x is concave down. And that's how you want to write it there. So hopefully that feels pretty comfortable. Then we have position functions, st, vt, at. So position, velocity, acceleration. Using any one of those designations, what I want you to do is see, when would you say the particle's at rest? When does it change direction? When is our velocity decreasing? What would have to be true on any of those in order for that to happen? This is generic. We're not solving for values, just trying to get a general answer here. So our particle is at rest anytime our velocity equals 0. Whether we change directions or not, if we have a 0 velocity, we're at rest. So that's what you'd be looking for. When do we change direction? That's when our velocity switches signs. So the first thing we would do is find out when are we at rest, and then check on either side of that to see if we actually switch signs. And when is our velocity decreasing? Our velocity will decrease when our acceleration is negative. Okay. Now that's different than speed decreasing. If it talked about speed, we would look at velocity and acceleration and see when our signs agree or disagree. But as far as this goes, that's what we're looking for here. Okay? So using the same designations, S of t, V of t, A of t, why don't you go ahead and see if you can answer these questions here. Okay, what is the average velocity of the particle? So our average velocity would be our change in position over change in time. So that would be position at 5, position 0 over 5 minus 0. That would give us an average velocity here. You can use the average value. Again, they're not going to ask you about average value stuff. So you could do that as well. They won't mark it off for you if you'd use something else, but either one of those ideas work. What's the average rate of change of the velocity? So now we want to know, how did velocity change? So we want to see what was the change in that velocity over that time. This would be the same as average acceleration. All right. When is the particle speeding up? Particle is going to speed up when velocity and acceleration have the same sign. So if they're both positive or both negative, then our particle is speeding up. And if the position at 1 second is 5, what's the position at 6? We would take our initial position of 5 plus the change in position from 1 to 6, which is the integration of velocity. So that would give us our position at 6. So hopefully, again, those feel pretty comfortable. Anything that doesn't, put that on your note sheet. You're good to go. All right, last thing in this part that we're going to talk about is related rates. So take a second, see if you can figure out at what rate the volume is changing for this. And we would say when the radius equals, we'll say 4 centimeters. So with related rates, what we're doing is taking the derivative with respect to some variable that usually isn't even there, right? So we're taking the change in volume with respect to time equals 4/3 pi is going to stay there. We're going to bring this 3 down, so it'll be 4/3 times pi times 3, which will give us 4 pi. When that 3 comes down, the radius will go to a squared then. So that's the derivative of like the outer function here. And then we're going to multiply by the derivative of r, which is dr dt. So that would be our initial derivative. And then what we're going to do is put 4 into there. We also probably need, I'm sorry if you paused this early and said, well, what the heck is the dr dt? Dr dt, we'll say, is 2 centimeters per second. So my apologies for that. Let's put all that in there. dv dt is equal to 4 pi times 16 times 2. And so that should give us 128 pi cubic centimeters per second. Okay. Now again, related rates, they probably have something similar to this. Probably not a whole lot of calculating to do because they don't want you wasting your time. They just want to see how much you know, but should be ready to go with something like that. So this is the end of part 2.